Hello, and welcome to the unit of Phys 1101 on using Newton's laws. So we've met Newton's first and second laws, but we haven't really used them to calculate anything yet. And particularly Newton's second law is a very powerful calculational tool, as we'll see. Here's an analogy for what we're doing for the rest of the course. If you start with forces, and those are your starting ingredients. So you know all the forces acting on some object, and you also know its mass. You can take those ingredients and cook them up with Newton's second law, and that tells you the acceleration. And if you have just one more ingredient that you add at this point, which is the initial velocity, you can determine or predict the rest of the motion of the object from that point on. Sometimes things get difficult though. Sometimes you have forces that change with time. And when that happens, it's very difficult to use Newton's second law, right? So it's not impossible, but you need calculus, and this is a non-calculus course. So in other words, what if your oven is broken? Well, there's a more modern kind of oven you can use, and that oven lets you bypass calculating the acceleration. You still need the initial velocity, but you can now get, again, to knowledge of the motion of the object. I will use this analogy for one more thing, though. If you taste a cake and you taste vanilla in it, you can infer that vanilla was one of the ingredients. By the same token, we'll sometimes use our knowledge of the motion of an object to infer things about the forces acting on it. But when you do that, you have to recognize the cause and effect relationship. The forces cause the acceleration, and the acceleration is responsible for the subsequent motion. Not the other way around. The motion doesn't cause the forces any more than you tasting vanilla in the cake caused the chef to put vanilla in it. That would be ridiculous. So remember that cause and effect relationship. Forces cause accelerations, never the other way around. Let's start to use these ideas to calculate things. And we're going to start off with one of these cases where we're going to use our knowledge of the motion, or in this case, the lack of motion. I'm going to say this crate hanging from this crane is stationary. We're going to use the lack of motion to infer what the tension in the cable is. So we're going from the motion, or lack thereof, to figure out the forces. So as usual, we're going to start off by figuring out what forces are acting on it and drawing the free body diagram. Well, the only thing in contact with the crate is the cable. And so we'll have a tension. You might say, well, wait a second, we want to know the tension in the cable. Why are you drawing a free body diagram of the crate? Well, that's the object we know about, and think about it. If you hang a heavier crate, the tension in the cable should increase. Clearly, it's the crate that is determining the tension in the cable. So let's draw this free body diagram. It's nice and simple. All we've got is the tension and the long-range weight force. That's it. So now think about F net. Well, the velocity is 0, but more importantly, the velocity is staying 0. Oh, the velocity isn't changing, the acceleration isn't changing, or the acceleration is 0, and so F net is 0. So I'm going to use the usual axes, and now notice, I could write the sum of the forces. That's the next thing we're going to do. We're going to use Newton's second law to use our information about the acceleration to infer the forces. So I'm going to say repeatedly, what we do now is we translate the free body diagram into a statement of Newton's second law. In other words, into a sum of forces. Now I could write T plus W is 0. And that's absolutely true. And I could say, oh, well, look, T is just Tj, and W is just negative Wj, and that's 0. Okay, but in practice, we don't write it that way. Look, all we're doing is adding up the y components. So we'll tend to say the sum of the y components is, and this would be just t minus w, and that's 0. And now we're basically done, because we don't know an equation for t, and we never will. T is determined out of Newton's second law from what we know about other forces, right? Remember, it's like a spring force. It can take on any value. And so we just solve for it out of Newton's second law. T is w, which is mg, which is 2,000 kilograms, times, and I'll use 10 for g, 10 meters per second squared. So there we go. That's 2 times 10 to the 3, 4, 2 times 10 to the 4 newtons. A case like this, where something is sitting still and its acceleration is 0, is called static equilibrium. And I'll just point out, I often see students after a while assume that the sum of forces is always 0. Well, no. The sum of forces is not 0. Newton's law says the sum of forces is the mass times acceleration. But it's just in a case like this, the acceleration is 0. Let's change something here now. Suppose that instead of being stationary, this crate is going at 1 meter per second up. Okay, the crane is pulling it up at a constant velocity. And let's see what changes. Now, I mean, your intuitive idea about this is probably that the tension must be greater. But let's see. It's going at a constant velocity up, isn't it? And nothing about the free body has changed. It's not touching anything else. And so all we have is the tension and the weight. And if the acceleration is 0, then F net is still 0. So nothing changed here. And remember that all we did was translate our free body diagram into our statement of Newton's second law. So nothing's changed there either. Well, now, instead of static equilibrium, this is an example of dynamic equilibrium. And look, the tension came out exactly the same because nothing at all changed. The velocity is irrelevant to what the force exerted by the cable is. Let's look at an example now that isn't equilibrium. We've got an elevator here and a package in it, and the elevator is accelerating at 2 meters per second squared up, and it's initially going 1 meter per second up. And let's figure out what force the floor is exerting on the package. So, again, I'm going to draw my circle around the package and note that the only thing touching it is the floor. And so I will have a normal force and perhaps some sort of friction, although it'll turn out there isn't any. And so I can draw my free body diagram. So I'm going to have the weight and the normal force. Note the normal force is perpendicular to the floor and it's a push, so it points up. And I'll come back to this issue of the friction in a second. So we have the normal and the weight. And we say, well, if the elevator is accelerating at 2 meters per second squared up, and presumably the package isn't falling through the floor, then the package must also be accelerating up at 2 meters per second squared. Otherwise, it wouldn't keep up with the elevator. So that tells us that the acceleration is up. And so F net is up. And once again, I'm just going to set my axes in the usual way. And we want to know this normal force. Now, if you've taken a previous physics course, you might be tempted just to write, oh, well, normal is mg. Normal is always mg, right? Well, hang on, careful. Check it out, because we've already seen normal force is also kind of like a spring force. So let's write our sum of forces in the y direction. We're going to have our normal and our weight And that now equals ma, the y component of ma. And so our normal is apparently the weight plus ma. Oh, okay, well, that's not mg, because this is mg plus may, and so that is our 10 kilograms times our 10 meters per second squared plus our 10 kilograms times our 2 meters per second squared. And so that's 100 plus 20, that's 120 newtons, whereas mg would have been just 100 newtons. What about that friction? Well, we know F net is straight up. And if there was a friction force, it would have to point one way or the other, right or left. There's no way F net could point straight up with an unopposed friction force pointing right or left. There would have to be some other force pointing the other way. And we've got no agent that could provide another force pointing the other way. So we know that there must be no friction force. One more. Let's say we're now pulling some box across the ice, and I want it to be ice so that I can ignore friction. So I'm going to say there's no friction. Of course there'd be some, but it would be small. And we're pulling it with a rope that's angled at a 30-degree angle up, and we're exerting a 15 Newton force on that rope. So again, let's draw the free body diagram. And I'm going to skip drawing that circle, okay? Because hopefully by now you're getting the idea that we think of the agents, the rope. The rope exerts a tension. The ice exerts a normal force, and it could exert a friction, but I've said it doesn't. And then we have our long-range weight force. And now we've accounted for all of our agents, and so that has to be all of the forces. And once again, I'm going to set my axes in the usual way. There's nothing funny going on here. But now you see I've got forces in both directions. So I'm going to have to sum up the x components of forces and the y components of forces separately. Right? This is vector addition I'm doing. And vector addition means you add the x components with the x components and the y's with the y's. Apples with apples, oranges with oranges. Well, the x components are easy. All there is the x component of the tension, Tx. That's it. And so that will be MAX. And then the vertical components, I'm going to have a vertical component of T, so I'll just call that Ty, and I'll have the normal force, and I'll have the weight, and I know its component is negative W, where W is its magnitude. And I don't know what the acceleration is, but I know it has to be horizontal. This isn't accelerating off the ice or into the ice, so this is 0. But now look, this, we don't need the y component here. This is perfectly solvable. We just have to do a little bit of trig for our Tx, which I've already done. So here it is if you want to check my math. All right, so there's the trig for T. And so now I can just solve for MAX. Right? So I'm gonna pull AX is just TX over M, or in other words, apparently over here 13 newtons over 10 kilograms, or 1.3 meters per second squared. And so now I'm done. The acceleration points right, and it's 1.3 meters per second squared. Now notice, in the previous problems, we were going from cases where we knew the motion and we were inferring forces. This time we're doing it the other way around. We know some forces and we're using it to infer the motion. And if we knew the initial velocity, we could now use this acceleration to figure out all the subsequent motion of this box.